Hi, welcome to this new video, which is going to be interesting because in this case, we are going to find the kinematic inertia ignoring the axial deformations. In the last video, we took this particular frame that we see in figure 1, and we told at each of these rigid joints, B and C, we require two translations and rotation degrees of freedom if we don't ignore axial deformations. And we also told the kinematic inertia will be equal to 6 in this case, right, if we don't ignore axial deformations. However, I also told if we want to ignore axial deformation just for column AB, I shouldn't have this V1 because if I have V1, it implies that this column can change its length. Therefore, I need to remove V1. What happens with this beam BC? U1 should be equal to U2 if I ignore axial deformation. It means I should either have U1 or U2 because those two are connected by this particular expression, right? So I'm going to show what happens if I ignore axial deformations, right? So I should directly remove V1 and instead of keeping U1 and U2, I should have either U1 or U2. That's what I'm depicting here in this figures 2 and 3. In figure 2, I'm just considering U1 rather than U2. And in figure 3, instead of keeping U1, I consider only U2 as independent, right? I can do either way. But in each of these cases, I should remove this degree of freedom, which is directed along the length of this particular column AB, right? Either way, I have only 1, 2, 3, 4 or 1, 2, 3, 4. Just these 4 degrees of freedom required if I ignore axial deformations, right? So the kinematic inertia instead of being 6 boils down to 4 if I ignore axial deformations, right? So we'll directly take those problems we considered earlier in the last video and we'll see what happens if I ignore axial deformation. The first problem, I mark those 3 degrees of freedom that are there at every rigid joint, right? That is both translation along with the rotation. And then here this is a guided roller, so I just have only a 7 degree of freedom, U5. These are the degrees of freedom which are required if I don't ignore axial deformations. Now, what does it mean to ignore axial deformation? We'll see. First, we start with this column AB. For this column, I should remove V1 if I am ignoring the axial deformation of this column AB. Only if I remove V1, then it implies that this column can't change its length, right? Similarly, what happens with BC? Now, if I already ignore V1 for this column BC, V2 should be absent. Only then this column can't change its length. So to summarize, for these columns AB and BC, what should happen? V1 should be equal to 0 and V2 should be equal to 0. If I say the axial deformations of column AB and BC are to be ignored, right? The same logic applies, what I apply here, to those columns at this right hand as well. That means V3 should be 0 and V4 should be 0. If I say these columns column EF and ED are actually rigid, right? So that's what we'll see next in the upcoming figure. Now, what happens with these two beams and these two levels? If we just consider the beam at this first level, B, U1 should be equal to U4 if I ignore axial deformation, right? To put otherwise, U4 minus U1 should be equal to 0. So either I should keep U1 or U4 as independent rather than keeping both of them as independent, right? The same applies here to this particular beam CD in this first level or second level, sorry. So I should either keep U2 or U3 as independent rather than considering both of them, right? To summarize, for columns AB, BC, EF, ED, this degrees of freedom should be 0, which are directed along the length of these columns. And then for beams EB and CD, U2 should be equal to U3 and U1 should be equal to U4. So I should consider only one of them as independent, right? So at this level, I am considering U1, right? And then at this level, I am just considering U2 as independent degrees of freedom, those horizontal degrees of freedom. So overall, just now we can sum up U1, theta 1, U2, theta 2, theta 3, and theta 4, and then U5. So finally, we have 7 degrees of freedom if we ignore axial deformations rather than 13, right? 13 was the kinematic inertia if axial deformations were there, right? Now we'll move on to the next problem. So this is a rigid joint. Those 3 degrees of freedom are required, and here we have a moment release, right? So these transition degrees of freedom are continuous. However, these rotational degrees of freedom are discontinuous. That's why we mark theta 2 beam and theta 2 column, right? Because these are independent now. And finally, this is a pin joint. So I have only this rotational degree of freedom committed here. These are the degrees of freedom which were there if axial deformations were there. Now, if I ignore axial deformations, for column AB, this V1 shouldn't be there. And for this column CD, this V2 shouldn't be there. And finally, for the beam BC, either U1 or U2 should be treated as independent, right? So you see here for columns AB and CD, V1 should be equal to 0 and V2 should be equal to 0. And finally, for the beam, U1 is equal to U2. So only one of them should be considered as independent. I am ignoring U2 and I am treating U1 as independent, right? So just sum them up 1, 2, 3, 4, 5. So kinematic indeterminacy in this case is 5 rather than 8 when we ignore axial deformations. Next problem. Here we have a lot of degrees of freedom. First I'm marking with rotation degrees of freedom, right? Then we will see what happens to the translation degree of freedom. Theta 1, theta 2, theta 3. See, I'm not showing this degrees of freedom that corresponds to column, right? I mean, see, I didn't mark these degrees of freedom. I'm just showing only those degrees of freedom which are required if I ignore axial deformations. Because if I ignore the axial deformations for column, these degrees of freedom can't exist, right? Because if those exist, then it means that these columns can change their lengths, right? So directly I'm starting with showing only those degrees of freedom required, right? So theta 1, theta 2, theta 3, theta 4, theta 5. Now this is a moment release. So all those members that are flaming into this joint can have independent rotations at this joint, right? So after theta 6, I mark theta 7 for this member, theta 8 for this member, theta 9 for this member, and finally, sorry, yeah, correct. The order was right, right? After theta 6, theta 7 for this member, right? Maybe this member, theta 8 for this member, theta 9 for this member, and theta 10 for this member. And then this is a rigid joint, so theta 11, theta 12 for this pin support, theta 13 for this rigid joint, theta 14 for this free end, theta 15 for this roller support, right? Those are those rotational degrees of freedom required. What about the horizontal degrees of freedom? So this is the roller support. This translation is permitted U1. Now here, if we come to the first level, I just require single degree of freedom, right? For all of them, because this is equal to this, right? This degree of freedom will be equal to this, and also this will be equal to this, and also this will be equal to this. So overall, I just require a single degree of freedom at this level, right? So I'm marking U2. Similarly, for this level, U3 is sufficient because this is a moment release. So anyway, continuity of horizontal degree of freedom would be there. So just U3 is required, and finally, and the last level, I just require U4, right? Those are the degrees of freedom, horizontal degrees of freedom required at every level, U1, U2, U3, U4, right? So this 4 stands for that. This 15 pertains to rotational degrees of freedom. Finally, see here at this joint, L, this degree of freedom is still possible, right? One may tend to forget this, so be careful. This V1 is still possible. This is a free end, right? So that also should be accounted for. Sum them up, you get a value of 20 contrasted with 36, right? So you get the kinematic index as 20 if we ignore axial deformations, all right? Now in this fourth problem, we mark the degrees of freedom without ignoring axial deformations. These 3 degrees of freedom at these 2 rigid joints, and this is a moment release. So only translational degrees of freedom are continuous, but the rotation degrees of freedom are discontinuous. So that's why I marked theta 2 left and theta 2 right here. Now, what does it mean to ignore axial deformations? For these two columns, it's straightforward. Directly, I need to ignore V1 and V3. How about these two members, this rafters BC and CD? Now, if I say the axial deformation should be ignored for these two members, BC and CD, it means that their lengths can't change even after deformation, right? So it boils down to these two expressions here. For this member BC, I would say its deformed length, that is U1 minus U2 whole square plus V1 minus V2 whole square with the square root should be equal to its initial length before undergoing deformation LBC, right? So that's what is written here. u1 minus u2 whole square plus v1 minus v2 whole square should be equal to lbc square. The same is applicable to this other member CD. So its deformed length should be equal to its initial length, right, before undergoing any deformation. So that's what it means. Therefore, if I consider v1 equal to 0, v3 equal to 0, I can also use those conditions here in these two expressions. If I do that, what should I remove? v1, v3 should be removed, and then I need to consider these two expressions, right? That's what I'm doing here. I am directly removing these 2 degrees of freedom. I did that already. And I need to consider these two reduced equations because I use the information that this degree of freedom and this degree of freedom are 0 in these two expressions. Now, here we see that out of these 4 degrees of freedom, I would require just 2 of them because once I treat U2 and V2 as independent, I can write U1 in terms of these 2 degrees of freedom, right? Similarly, U3 can be expressed in terms of U2 and V2 if I treat U2 and V2 are independent, right? So I don't require these 4, right? Rather, I just require only 2 of them, which are U2 and V2, right? Hence, theta 1, theta 3, theta to left, theta to right, right? Along with these 2 transitional degrees of freedom or the independent degrees of freedom if I ignore axial deformations, right? So in this case, the kinematic velocity will be equal to 6 rather than 10. Fine. So we'll see the last problem. Here I start with marking the rotational degrees of freedom. First for rigid joints 1, 2, 3, 4, 7, 8, 9, 10. Right? Along the boundary I just marked. Now we'll move to this releases here. First here I have a moment release, so there is a slope discontinuity over here, which means these two will be independent. How about these two releases? This is a shear release, slope continuity is there, and then this is an axial release. Again, I have slope continuity over here, right? So if I consider only this rotation degrees of freedom, 12 of them are there totally, so I use 12 here. Next, what about those degrees of freedom along x-axis? Those are represented with the letter U. So this is a guide roller support, U1 is possible. Here, if I come to the first level, just I require only U2. Now, if I come to this second level, we need to be very cautious because we have an axial release here, right? Because of the presence of axial release, these two ends can undergo independent translations along x-axis, right? Which means this should be treated as a single element and this should be treated as a single element. Now, for this CM to not undergo any axial deformation, this degree of freedom and this degree of freedom should be same, right? So I just require only one of them. So I am using this. Similarly, if I come to this member Mi, as now this can independently move, this degree of freedom should be equal to this for this member to be axially rigid, Mi to be axially rigid. So I just require either this or this, right? I am just using U3 here. So at this level, I require 2 translation degrees of freedom, which are directed along x-axis, right? So I require one for this separately and one for this separately. That's why U3 and U4. But if I move on to this next 2 levels, I just require only one translation degree of freedom directed along x-axis because these releases do not introduce any discontinuity of U, right? This translation degree of freedom over here will be continuous. So I just require only U5 and U6 at these 2 levels, right? So that's why you have 6 used here. And finally, how about those translation degrees of freedom along y-axis? I just need to consider this releases here. It's a moment release, just I require only V1 here because the transverse displacement will be continuous here. Similarly, here the transverse displacement will be continuous, so I just require 1 degree of freedom, so I mark V4. However, this is shear release, which causes discontinuity of transverse displacement. Therefore, I should have these two independently marked here, so V2 and V3. So overall, V1, one for moment release, 2 of them for shear release, and then 1 for axial release. 4, those 4 used here. So 12 plus 6 plus 4, you got a value of 22 rather than 37 if I ignore axial deformations. That's all. Hope this helps. Thank you so much for your passion listening.